a good day. So we'll start with the basic flow cytometer training, where I'll take you through the information about the flow cytometer and a little bit knowledge of the CST. What does CST mean? What we check in CST, and also we are going to the application part of it. So I'll try to finish it off by 1 p.m. But let's see. And sorry, I wanted to make it bit interactive, but let's see. If you have any question, you can write in the chat box and there we can address your question. I'll be sharing my screen, so give me just 1 minute. I hope I'm audible to everyone. Maybe you can write a message if I'm audible.
Yes, you are audible.
Yeah, thank you. I'll be sharing my screen in just 1 minute. Can you see my screen?
Yes, we can. No, actually, no, your
Okay,
screen is not visible. Just, yeah, now we can see your screen.
you can see it. Okay,
Yes.
fine.
Go to the full screen mode if you want. Yeah, that's fine.
Yeah, now it's fine. Okay.
Yes.
Uh, so good morning, everyone. I am Naman Goswami. I'm from BD Bioscience and I'm an application specialist here. So today we'll be talking about the basic of flow cytometer. What does flow cytometer means? What it can do? What application we have? And a lot of things we're going to discuss in this session. So let's just talk with the basic of flow cytometer. What does a flow cytometer mean? What is the definition? What is the FCM tells you, like, and how does it work? So let's go to the basic definition. It's just a vague definition. We break the term flow, cyto, and metry. So flow means anything which is in motion in the stream, and then cell means cyto means your cells. Metry means measurement. So just in a very simple term, the flow cytometer is a measurement of either cell or any particle when it's in the flow or in a stream, that we call flow cytometer. And if you go to the definition, it tells you that flow cytometer is a technology which simultaneously measures them and analyze multiple physical character of single particle, usually cell. Why we use particle? Other than cell, for example, we use beads, we use other particles, we use nanoparticles also, we can do that as well. But generally we use cells. That's why we are using as a cells here. And when it's in a flow stream and through a beam of light. Now in your flow cytometer, we have a key term called forward side uh, side forward scatter, side scatter, and then your fluorescence intensity. What does flow cytometer tells you? It tells you the relative size, the relative granularity, and the relative fluorescence with the help of forward scatter, side scatter, and your fluorescence intensity. Basically, fluorescence intensity from the other detectors, for example, a red channel detector or a blue channel detector. Okay, now how it detect the invert principle flow scatter forward scattered work, invert principle side scattered work. So forward scattered work in diffraction of light, and your side scatter worked in reflection or refraction of light. What does it mean? So let's take an example of the forward scatter. For example, uh, when there is a cell in the path of in the stream, and the forward scatter is always at the in front of the incident ray. So when the light will come, it will hit the cell, it will diffract the light, and that light will capture by the detector, and then it will convert into a signal. And through that, you'll get to know what is the size of the cell. For example, if it's small, the bending of the light, the diffraction of the light is very less, right? And if it's large, then if you can see here, the diffraction of light is too much. So that's how, or you can take example of a torch. When you have a small bulb, then you get a small light, and if you have a big bulb, you get a big light. So it's the same concept here. Then let's go to the side scatter. In side scatter, we have we it worked on reflection and refraction. So as you can see, uh, so it's tell you the granularity, as I have mentioned before, the granularity. So more the granule of the if a cell is more granule, or it is more complex from inside, it has a lot of thing inside its cytoplasm, then what's gonna happen is light will come, it will hit, and either it will reflect back or refract back because of the change in the medium. It will tell you like how granule is the cell, what is the granularity of the cell. But again, all of these things are relative. It never tells you the exact size or exact granularity. What does it mean? I'll be going forward and I'll tell you what does it mean basically. So for example, in this slide, this is a human whole blood after RBC lysis. So what does the relative size and relative granularity mean here? So these scales are arbitrary scales. They don't have any measurement. It's just a scale to show you that your population is coming under this much and that much. But let's talk about the size now. So forward scatters tell you the relative size. Relative size means in heterogeneous population. So it's a heterogeneous population where you have your neutrophils, your monocytes, and your lymphocytes. In that heterogeneous population, you can tell that lymphocytes are comparatively smaller than your monocytes, and lymphocytes are comparatively smaller than your monocyte and the neutrocyte, because the site scatter of the lymphocyte is smaller than all of those two. Then let's talk about the granularity. And as you know, in biology, neutrophils are more granule than lymphocytes and monocytes. They have a more granularity. So you see their site scatter is far, far, far higher than the lymphocyte and the uh, monocytes. That's how we tell the relative size or relative granularity. Now this is the heterogeneous population. Let's come to the homogeneous. If you have a homogeneous population, let's say you are just talking about the lymphocyte, at that time, how will get to know like is it small or is it big? In that scenario, you should have a control. Let's say if you have treated your lymphocyte with something, then you should have an unstained or let's say untreated control. You get to know whether it's affecting the size of that particular cell or not. And what's the range of particle you can detect in flow cytometer? So it's go from 1 micrometer to 100 micrometer, but generally most of the flow cytometer detect a size of 1 to 70. And also you can detect the absolute size, but when point come the absolute, there they use something called the beads. Or let's say if you want to get the absolute count, absolute value, at that time they need something which we call the bead. In this case, they are using some bead. Uh, this method is very useful in case of extra exosome studies and all. People are now these days are using this exosome studies. So now let's come to the fluorescence. You must have learned in your 12th class that every particle has its ground state, and when it absorbs the energy, it go to its excited state. And then after a point of time, because it won't be staying there for long, So it will come back to its original state, but when it will come back, it will release some energy. What and how does it help us here? So basically, let's talk about a fluorescence or a fluorochrome. A fluorochrome, and the best example I would give you is, if you have seen in, in roads, when you put the beam of your light from your car, those, bright color things give you some light when you put the light on them. So that is the fluorochrome. They are made up of your fluorochromes. So same thing, same principle, we use it here. uh, so now your particle or a fluorochrome absorb the light from in its ground state, and then it will go to its excited state, then it will come back and emit some light. So a light always have energy and wavelength. And if you see, let me put this in pointer mode. Yeah. If you see this one, E is equal to sc over lambda. So light has energy as well as wavelength. So, and energy is inversely proportional to your wavelength. So right now, in this case, the wavelength is low because the energy is high. That's why if we take an example of FITC fluorochrome, it's excite at 488 nanometer. So if you go and check again in your literature or study, you'll always get to know that the excitation wavelength is always lesser than your emission wavelength, because the energy is higher at that point, and when it will come back to its original state from the excited state, then the energy, it will lose some energy because of the vibration, because of some photon emission. So now the energy is lower than the its ground state, or like from the excited state. When it will come back, the energy is lower, so that's why the wavelength is high. That's why your excitation wavelength is lower. Let's say if we talk about FITC, it excite at 488, and then it emit at 530 nanometer. Okay, so it's mean the emission is always lower, greater than your excitation, and excitation is always lesser than your emission. That's how we get the graphs. That's how we get the fluorochromes. Okay, so this is just a basic example or a basic definition of the fluorochromes. I hope you understand that. Now let's talk about the basic component flow of a flow cytometer. Any flow cytometer, whether it's BD, whether it's Beckman, whether it's uh, any company, Thermo, any flow cytometer, all of them have these three basic components, which is fluidics, optics, and electronics. And these are the important. It's like we have brain, heart, and other important organ in our body. Same is these parts for the flow cytometer. What does fluidics have? Fluidics has the cell suspension, and it will give you your cell in a single flow, or eh, whatever coming in the flow, it comes in the fluidics. And your optics, like a illumination path where your lasers, and then your after the illumination, the photon will generate, the photon will get collected, all of these things come in your optics. Then comes your electronics. In electronics, and the photon is already collected somewhere, then you have to turn that into a signal. That's the part of your electronics. So this is just an overview for the flow cytometer. How does it work? And I really want you to keep this overview in your mind, so it will be very helpful for you when when I'll be talking about more things in next slides. So this is like a path of the light. This is your interrogation point. What does interrogation point means? Where your cell will hit the laser, and then it will release the photons. The point where your cell hit the laser, that we call the interrogation point. So just want to inform you that tomorrow I'll be coming there and I will ask you this question. So let's see if you remember this. Just because this is one of the important point, because whenever you go for, like in your future, you'll go for any flow cytometer talk, or anywhere, they'll use this terminology interrogation point, and don't be confused. It's just a simple word that it the point where your laser hit the cells, So your cells from flow cell, it will go upside, and where the cell will hit the laser first, that is called the interrogation point. Then this is your excitation optics, this is your collection optics, this is your electronics. What does it mean? I'll be talking more about it in next slides. So what's happening in flow cytometer? In fluidics, cells are in suspension, and it's going inside the machine in a single profile, in a single file. What does it mean? That one by one it's going in the machine. And then there is a focus laser which is hitting the cells, that what we call interrogation. Then after the interrogation, the photon are releasing, then the signal is releasing, and those signals are converting into a electronic signal. That what the electronic part do, interpretation. You got your after electronics in your software, you got it in your graph format, and then you interpret whether your, let's say if we are talking about lymphocyte, and in lymphocyte we are talking about CD3 and CD4. There you'll see, then you'll interpret it that this much of cells are CD3, this much of cells are CD4, or whether we have that particular cells or not. That's a part of interpretation. So let's talk about the fluidics. So this is just a basic overview of a fluidics. What does fluidics have? Or I would say, let's just open the machine. And when we'll open the machine, I mean, I can't do that, but I'm just making you imagine that. And when you'll open the machine, you'll find something like this in your machine. And so as you guys have lyric, tomorrow I'm going to show you that as well. But just for your information, keep this in your mind, that it will be very helpful when I'm going to explain you more things in machine. So this is your air filter, uh, and then this is your air pump, then sheath regulator, sheath filter. What does it mean? uh, this is a filter which is there in your machine. It's connected to your air, and this is your sheath filter. This one, if you have seen your uh, lyric, there the white color plastic thing is there on the left hand side of the machine. That is a sheath filter. And this is a sheath regulator. It regulates the sheath pressure. And then there is a sample regulator. It regulates the sample pressure. So there are two type of pressure in the fluidics or in the machine. One is sheath pressure, another one is sample pressure. So there is one question from my side to you guys. Okay, what this regulator do first? It regulate the pressure. It make the flow. It continue the flow in inside the machine, and also the sample regulate continue the flow of the sample inside the machine. Okay. Now let me ask you this question. I really want to ask you this question that you can write in the chat box. Uh, which pressure should be more? The sheath pressure or a sample pressure? Let's see if I can see the chat box here. Yeah. So Hasib ji has given sample pressure. Uh, Arpita Das has given sheath pressure. And else sheath pressure, Kiran. Okay. Nandita sheath pressure. Okay. Sumit ji sample pressure. Okay. Okay. Nice. Thanks for the response, guys. Uh, so I want to congratulate them who have taken the option of sample pressure. Now let's why not sheath pressure? Many of them are thinking of that as well. Okay, let me tell you why not sheath pressure and why the sample pressure. Uh, just a minute. I think you won't. Yeah, can you see my screen? Can anyone tell me, please? Uh,
Yes, 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 yes.
yes, yes. So why not sheet pressure? Why sample pressure? The answer is pretty simple. That if the sample pressure is lower than the sheet pressure maintain inside the machine, it is flowing this sheet inside the machine. And if your sample pressure is lower than your sheet pressure, then your sample will not go in, right? It's like if the pressure is more here and less here, then it won't take the sample in because it is already forcing it to go back. So it will not take your sample in. And now, I hope it's clear to all. Uh, Now let's talk about again. There are few more things uh, in your sample pressure and sheet pressure. Your sheet pressure always remain constant, but your sample pressure you can change it. We give you option for that. You have high, low, high, medium, and low. You can change your sample pressure, but even the low sample pressure is higher than your sheet pressure. So let's say if it's 5 psi inside the machine, then your sample low pressure will be somewhere around 5.1, 5.2. Okay, so at least the sample will go in. I'll be talking in detail more in like upcoming slides. Let's go to the hydrodynamic focusing, or what is happening in the fluidics. So what does hydrodynamic focusing mean? The introduction of one smoothly flowing stream or fluid into the center of another smoothly flowing stream in such a way that it will make a funnel-like structure or a focused, a focused axis. At that time, whatever is, whatever is focusing, it make a funnel-shaped structure that we call a hydrodynamic focusing. Okay. Now, just a minute. Okay. So, how does this hydrodynamic help us? So, your cell should hit the laser one by one. So, you'll get, again, flow cytometer is a technique which tells you the property of an individual cell. Like a cell hit the laser one by one, and then it will tell you the, okay, this cell is this much, having a this much of fluorescence, this much of size, a relative size, I would say. So it should hit one by one. If it will not hit one by one, what's gonna happen, that also I'm going to tell you. But let's just to make it a very narrow path and a very focused part. That's why this hydrodynamic focusing is important. Now, as they have uh, uh, told here that one liquid, this is your sheath, and inside that liquid there is another liquid, and no tubing are there. It's just a two liquid, and in such a way that they are maintaining the laminar, and because of the laminar flow, there is a hydrodynamic focusing of that particular liquid which is inside another liquid. I know it's a bit confusing. It might be a bit confusing for you guys, but let's just focus more in this, that these are these both of these are liquid, not a tubing. Both of these are liquid. And as the laminar flow or laminar law says that, well, if your Reynolds number is equal to 2000, and then your velocity is same, then the flow will be the laminar flow. It won't be a turbulent flow. And if you have a laminar flow, these two liquid never mix to each other. It will be flowing in a separate velocity, in a separate pace, and they will not flow, they will not mix with each other, and they have their own path. Okay, so this is a fluidics part. And now, as I was talking about the sample pressure, so they have discussed here in like two form, like low and high. So what does low means, what does high means? When you have a low sample pressure, so there are three mode in your machine, actually four. So one is your low, then in low, the amount of sample or the amount of your let's say sample go is like 12 microliter per minute, and in medium in lyric it's goes 60 microliter per minute, and high means 120 microliter per minute in lyric. In and there is one another mode, it is called high sensitive mode. In that it goes somewhere around 50 microliter per minute. Okay, so what happened in low pressure, the core size is small, so it is letting one cell one by one, it's letting the cell go inside the machine, or then there in into your interrogation point it will hit one by one. But in your high differential pressure or high sample pressure, the core size has increased, and now you see there is a zigzag motion of the cells. Also, at one time, multiple cells are going in. Because of that, there is very high chances that either you'll get uh, your doublets or multiple cell, or not just I won't say multiple, but let's say two or three cell will hit the laser at one time, because then it will go like one cell this, one cell this, and they move like this, right? Or maybe they are stick together and they move like that. So in that scenario you might find a lot of doublet in your population. But so that's why there is. And what does it mean? What is the problem with high, low, and I mean, what is the compromise you have to do with high, low, and medium? So in low, your resolution is pretty good because at single time, single cell is hitting the laser. But as you increase the uh, sample pressure, then it will give you a little bit of background and a spreaded population. It's because multiple cells are hitting the laser at one time, or uh, there is a zigzag motion, they are not stable. But then the question comes, why we need these three options? Then we could have done the uh, low sample pressure. Why we are going to high or medium? Then let's take a case where you have a lot of cells. And one of my colleague has a favorite dialogue: if you want to finish your PhD in 5 years, uh, then you need high. And if you want to finish your PhD in 7 or 10 years, then you need low. So in that scenario, when you have a cell with a very high concentration, or let's say you have a 1 ml of sample, and in that case, you know that your population is, you can differentiate your population. Even there will be a small spread, still you can differentiate your population. In that scenario, you can run in high and medium as well. But let's say when you have a population where you can't play with your resolution, you need it with a high resolution, means your negative should be separate, your positive should be separate. And when this come, it's come in case of your cell cycle. There it is very important to resolve your population. Why? Because let's say at a one, when you have like high sample pressure, at that time, as I told you, like multiple cells, or let's say two cells are going together, like they are stick together and then they are going. So in cell cycle there are phases called G1, G0, and then your G2 phase, where it's because of the DNA and all. So though there is two cells sticking together, they are in G1 phase, but that will show you as a G2 phase. So that's why it's very important to keep your pressure low at that time. In some particular experiment, you have to keep your sample pressure low. High sensitive is again in between your medium and low. So that is for when you want your sample to be run in like some good amount of speed, but then you also want it to be, uh, in a bit more resolved, you want a bit more resolved population. Now this is your sample introduction point, where you put your or we call it sample injection port. It's different people use different terminology. There you put your tubes in your lyric, it comes without any support, but in your other machines it comes with a support, because in Lyric it's there are this vacuum pump which help in sticking the tube. Also, it comes with an adapter where you can use 50 ml Falcon, 15 ml Falcon, and then your 2 ml up and drop. SIT flush, it is also in your fluidics. SIT flush means you are running the sheath inside the machine. And let's say if you have any clog in your flow cell, then by running the SIT flush, it will force this sheet to go inside your sample uh, tubing or a sample core, and it will also wash your probe. So basically, it's a washing step. When you think your flow cell is a bit dirty, then it's a washing step there. Now let's go to the optics part. In optics, you have again, as I told you, you have two optics, excitation optics and then your collection optics. In excitation optics, you have laser and filters and mirror. In your collection optics, you have fiber optic cable and then your PMTs and then your then your filters. Uh, Now, let's come to the excitation optics part. So this is it has laser as well as prism. First, I'll tell you what does this prism and mirror do. So you have a laser. Though laser is a single pointed, but still you want to focus it. That's why we have prism and you can say lens, not mirrors, prism and lens. It will even more focus that laser light. Now I have a question, though you can see it here, but still I want to see how many of you can, or I move this slide and I want to ask you, we are using laser here. Why not LEDs? Can anyone give me the answer? We can use LEDs instead of laser, right? But why laser? Why not LEDs and other types of or other source of light? Can anyone answer that? Oh, nice. Singh has said laser is a coherent source. Okay, I apologize to ask you this, but Neha, can you please open your mic and tell me what does this coherent source means? It's a great answer. I was expecting this. Uh, if you can open your mic and tell me like why the coherent source, what does this coherent source means? If possible, no worries. If not, I'm just okay. I'll tell you. Great answer. I really wanted to hear that answer. So again, laser is a coherent source, single wavelength of light, though even LEDs can go for single wavelength. The main part is coherent source. What does this coherent source means? Coherent source means if the light is in, it will give you the wavelength or a wave just in a single form, either in crust form, either in trough form. It won't be like fluctuating, right? Because in wave you find two forms, crust and trough. So whether if your laser or if your light is in trough form, then it will be in trough form. If it's in crust form, then it will be in crust form. Okay, so that is what coherent source means. Then they are they can generate light in just very small amount of output or like power, and they are not that much of expensive. uh, Generally in flow cytometer we use solid state laser because they are quite they have a good shelf life. They can go for like longer time. In just one case we use in red laser we use a gas laser. These are the analyzer we have in our BD, and now one more and few more are there now. We have recently launched our new advanced flow cytometer, which we call the Discover Acid. It's like a next generation flow cytometer that's gonna change the whole scenario of flow cytometer. There you can do the cell imaging as well. Means when the cell is passing through your flow cell, you can see your cell as well, how it's look like. So that's gonna change the whole, whole flow cytometer world. Also, it is a spectral flow cytometer. Generally, in for example, in your lyric, I don't know how many color you can do, but the maximum color in lyric you can go up to 12 color. But in discover, you can go up to 80 color. Imagine, let's say in one go, in one cell, you can see 80 different marker. How cool it will be. Um, Now let's go to the collection optics. So in your collection optics, you have your uh, quartz flow cells, optical coupled to the quartz flow cells. So you have a focusing lens, you have dichroic mirrors and optical filters, and then your detectors, light sensitive diodes and photo multiplier tubes. What does the filters means? So there are three types of filters in general flow cytometer: long pass, short pass, and band pass. Um, it's better you note this one because it will be very helpful for you when you are going to run your, you are planning to design your experiment in flow cytometer. You should have a knowledge about this filter so you can, perform your essay in flow cytometer. If you don't have knowledge about this, it will be hard for you to perform it because then you won't be able to finalize your panel in that in flow cytometer. So long pass means what does long pass means? Any, let's say long pass 500, any light which has a wavelength of more than 500, that particular filter will let that light pass through it, transmit through it, and other it will reflect back. And opposite of your long pass is your short pass. Any light which is smaller than 500 or shorter than 500 wavelength or 500 nanometer wavelength, it will let it pass through it, and higher wavelength it will reflect back. And now comes the band pass. Now, so band pass, as you see, 500 by 50, and you must have seen in your flow cytometer that first come the long pass and then your band pass. And what does this 50 mean? So don't get confused that it is, toward 50, like plus 50, minus 50. No. First, always remember when you see band pass 500 by 50 or any other where they have given this value, you have to make it half and then put it toward plus side and minus side. So it's half of it plus side and half of it minus side. So it can form a band, like this kind of band. You see this? So it's telling you that it will let pass, it will only pass those wavelength or those light which are coming. So 450, which are in between 475, which are from 475 to 525. It will only let that laser or that light pass through it. Other than that, it will reflect back. And this is very important to get the crisp data, to get the proper signal. That's why they are using this kind of filter. Now, what does the dichroic mirror do? uh, it bend your light, it reflect the light at 45-degree, and other light it transmit it back. So let's talk about the optical filter layout. This is a herringbone pattern, which was there or still there in machines other than BD. Um, so in this pattern, light will hit one by one to another, detect another filters. Basically, it works more in the transmission principle, like your uh, your signal will pass through one filter and then it will pass to another filter, then it will pass through another filter, and then let's say they are using long pass filter here, and dichroic mirror, long pass dichroic mirror here. So it will let the 500 nanometer, greater than light, greater than 500 nanometer, it will let it go, uh, uh, pass through it, and other it will reflect back. But when there is a lot of transmission happening at that time, there is a loss of signal. So PD come up with something called octagon or trigon pattern, which works in the reflective layout. What does this reflective layout means? I'll tell you more in like forward slides. Now, this is a patented technology which BD use. No other machine use that. That's why BD use the PMT, still use the PMTs, uh, PMTs, because as some people, from the other companies tell that they are using the best detector, they are using the ARD's detectors. But the case is, even if they are using the ARD detectors, still it's not good enough, because still it's work in the transmittance. And if you see this data, uh, I have if you see this data, there was study done by people itself, I think it's from BD itself. They have shown that the reflectance work better than the transmittance. And now let's talk about what does the reflectance means. So also, in this octagon and trigon pattern, what happen is, first, the wavelength which is higher, means which has the lower energy, it will hit the first detector. And then another detector which is lower than that, then another detector which is lower than that, then another detector which is lower than that. So there will be a conservation of energy. And if there is a conservation of energy, you won't lose your signal, because again, it is hitting that detector or that filter first, which has the lower energy. So there will be no loss of energy. And if there is no loss of energy, then there is no loss of your signal, because again, your signal is made up of your photons, right? And those photon, if you are not losing those photons, then you are getting, let's say, if you are giving 10 photon, then you are getting a signal of 10 photon, not 5 or 8. uh, So you have two type of detector, photodiodes and photomultiplier tubes. Photomultiplier tubes are placed for your side detectors and then for your fluorescence detectors. And your photodiode is there for your forward detector. Why? So basically, photodiode is a weak detector. But why we use weak detector in forward scatter? Because forward scatter, if you remember that flow diagram, in that flows detector was in the place of the light. So it was so close to the interrogation point that it don't need much of something like which can, because already it's getting a lot of uh, photons. There is no loss of data there, so we can use a weak detector there. But now comes the photomultiplier tubes. They are expensive and uh, high signal, like uh, I would say advanced detectors, which can detect even the smallest amount of the photon. So we use this detector in our fluorescence fluorescence detectors, where your blue, red, and violet laser will hit, like the signal will come. And also for the side detector, because they are a bit far away from your point of interrogation. This is a general overview how it's look like. So these are your laser excitation optics. Here comes the lens and the prism. This is your excitation optics. It will focus the light. And then this is your forward scattered detector or diode. And then these are your optical fiber, same like the geo use in their technology. It's the same optical fiber. And you must have learned in your physics that optical fiber has a property that it let the proper signal pass through it, a light signal pass through it. And these are your laser detectors, violet, red, and blue. Uh, so that's why they are, as you see, they are a bit far away from your interrogation point. So you need some strong detector to detect those signals, so you won't lose anything. Now, again, this is, as I mentioned, that the light will come and it will first hit the higher wavelength, means the lower energy, so the energy will conserve. And now, as I have showed you, this is 752 long pass. So any wavelength which is greater than 752, it will pass and other will reflect back. And once it will reflect back, it will go to your another detector or another filter, which is lower than that. And then same pattern will follow. And now this thing is working in the reflectance. As you see, first it will come and it will reflect those wavelengths which are lower than this, then those wavelengths which are lower than this. So basically it is working on your reflectance. In other machine or other company machine, what's happening is, in if I'll go back to Haricom pattern and just keep that thing in mind now, first it was hitting this, there was nothing like a reflectance. Whatever reflectance was happening with this mirror, that signal is going here, then it will transmit through the filter or mirror, then it will go here, then it will reflect few signal here, then it will go here. So in the end, whatever signal you'll get in this detector, it will be very weak, right? Because uh, when the transmittance happen, it absorbs some of its energy, some of the photon get absorbed by that mirror itself. But in reflectance, most of that, if you must have if you remember, there was in your physics we used to tell that if something passed through something, then it will absorb a little bit of photon of that. But in reflectance, there are a very less photons than the transmittance. So that's the principle they have used here, and they have showed it here also through some data, that in transmittance, this blue is transmittance, you are losing some of your data or some of your photons. Fluorochrome or fluorescence, I already discussed, and I already told you what does it mean, and why it is necessary. It's necessary when your sample tagged with a fluorochrome hit it here, so it will, so again it's a fluorochrome, it absorb the light, it will go to its excited state, come back to its ground state. At that time it will emit some energy. That energy comes in a terms of photon, in a packet of photon, and those photon will transfer here, and that's how you get your signals. So this is the absorption spectrum of a fluorochrome. If you remember, I told you like in FITC it's go for like 488 and it excited, and then this is for APC, which is your 630, 640 nanometer. And this is your emission spectrum. For FITC it's come 530 maximum wavelength. For P come 585. Per CP somewhere around 685, something like that. So this is your emission. Now, again, this is again the emission spectrum uh, for multiple colors. Now, let's come. Now, what does the fluorescence tell you? Generally, we put the fluorochrome in the antibody. So your antibody is labeled with the fluorochrome. So more the binding site, more will be the fluorescence. If you have a more fluorescence, it tells you that there are more binding site of that particular marker in your particular cells. For example, they have given this example: granulocyte and lymphocyte. CD45 is much has a high CD45 is too much in lymphocyte compared to your granulocyte. So there will be a much more fluorescence generation, or fluorescence intensity is much more in lymphocyte than your granulocyte. And that you can see in your graph as well. So fluorescence intensity will tell you the binding site, number of binding site, like not exactly the amount, but it will tell you that yes, this particular cell has more binding site than your, let's say, other cells. Now, in how many format you can see your fluorescence data. in what form it will be display. It will be display uh, in your histogram when you are using a single fluorochrome, and dot plot when you are using a multiple fluorochrome or more than one. This is again example of your fluorochrome, and basically fluorochrome binding, or your binding sites. So as they have labeled it with, they have used antibody CD45. These are your lymphocyte, monocyte, and neutrophils. As you see in your lymphocyte, you have much more binding sites for CD45. That's why the fluorochrome intensity, the fluorescence intensity is high in lymphocyte compared to your monocytes and your neutrophils. So far we learned about uh, illumination region with the excitation optics, how the cell are passing through the uh, uh, through a single profiling. How does hydrodynamic focusing work? What does the uh, uh, optical things do? How what are the PMTs and all? I also, I forgot to mention you that the PMTs are photomultiplier tubes. They worked in, for example, you have RT-PCR or a PCR in your lab. It amplify the data, right? You give a amplicon and it amplify the particular amplicon. Same goes for PMTs. PMTs or photomultiplier tubes. When one photon hit it, it convert those photon to the electrons. And not just it convert it, it will amplify it. Let's say if one photon is one, just a vague example, one photon is hitting to the photomultiplier tube, it will release somewhere around 10 or more than that electron. So basically it will uh, amplify your signal as well. And if you have done any experiment in flow cytometer, and you have, you used to change, or you change some voltage, and what does those voltage do? You are basically giving or taking away those voltage from the PMTs. Either you are giving high voltage or low voltage to those PMTs to play with your signals. The more voltage you do, the more amplification happen, and the more signal you'll get. That's why it's very important to adjust those, voltages, so you won't get a, unwanted signal, or you get a proper signal. That's why the uh, PMT voltage adjustment is important. So now let's come to the electronic part. In your electronic part, the analog signal uh, convert into the digital signal, then you get it in a area and height. So there is a pulse formation there. Then you can do the compensation and calculation. I'll come to that part also. Now, what's happening? So you see the data there, right? You see a data in your PC, but how the data is generating, what is going inside the computer, what is going inside the machine, like we are seeing those graphs, but how these graphs generally have, like how they are making this graph, how the things are happening. So this is the answer for that. So let's just give you one example. First, when the cell will come, this is your interrogation point, a laser. Draw it for you here. If your sample tube is here, okay, and your sample is going up, this is the sample direction, right? As you can see, this is your sample direction. So uh, now your sample is going up. It will hit the laser first. When it will hit the laser, so there will be a voltage time graph, and it will generate some signal. And when it will, like a little bit of signal, and when it will be inside the laser, it will give you the maximum signal. And once it will, get out of the laser, then the signal will go down, right? So how this thing help us now? It will make a graph as you can see here. Okay, it is forming a signal and then it's going back. So it is like when it get out of the laser, the signal comes down. So through that, so basically they are using a simple math there. You'll get a voltage height or pulse height, you get a pulse width, and you get a pulse area. And so generally we get the pulse height and pulse area, and through that they calculate the pulse width using some mathematical calculation, like width is equal to area divided by height. And this is, and through this they give you, I'll tell you. So through this area, width, and height calculation, they tells you the uh like what is the size of the cell, a relative size of the cell, a relative granularity of the cell, a relative fluorescence intensity of the cell. All of these things are coming through this particular pattern. And how? So, so for example, if you take this example, this is again a lysed blood, and this is your lymphocyte, monocytes, and granulocyte. If you remember, I told you the relative size and relative granularity. So if the size is small, then the forward scattered is less. And if it's big, then the forward scattered is more. And if the granularity is high, then then the side scattered is more. Let's just take the example. See, the sorry. uh, the size of the lymphocyte is small. So even if you see the voltage, the pulse here have formed is very small. Like the area of those or the area height and width of those pulses are very small. Now let's go to the monocyte. The side scatter is bit high. So, or sorry, forward scatter is bit high, but side scatter is almost the same. So if you see the pulse, it's bigger than your lymphocyte. And when we goes to the your neutrophils, then the SSC pulse is quite big. That's how they interpret the data. And this voltage thing is also important when you do the doublet discrimination. It is important there also. So what is happening inside the machine? These things are converting into this. How it's happening? You gave your signal. The sun is your sample tagged with the fluorochrome antibody, and those antibody after hitting with the laser giving you the photon. Now those photon are getting amplified through your PMTs, and then AADC and digital signal processor, they are converting the, so what does your AADC do? It convert the digital signal in sorry analog signal into digital signal, and then it processing the signal, and you are getting these values. Again, this is the same thing, like digital pulse happen, then they process the pulse, and the PMT voltage I was talking about, this is your PMT voltage. The more PMT voltage you give, the more signal you'll get. But again, it is very important to optimize your PMTs, uh, to optimize the voltage. Otherwise, you might end up losing it. Let's say, if you think like I'll give uh, a good amount of PMT voltage, that I'll get a good signal somewhere around 10 raised to power 5, but it will shift your negative population also. And in some cases, you'll lose your signal. It will go out of your scale. So that's why it is very important to adjust your PMT. I'm going to show you tomorrow like how you do that. Maybe some of you know that, but I'm going to show you tomorrow like how you do the PMTs, how you can do that, how you change the voltage and how important it is. And then this is the processing happening inside the machine, and then in the end you are getting something like this, data like this. What are the advantage? So advantage are no dead time, means the time you are acquiring the sample, at the same time you are getting your data as well. You can use threshold. I'm going to talk about this later. Compensation you can do also. What does compensation mean? That also I'll come later. Post compensation, you can do ratio of any parameters, which means you can do area versus height of any parameter, like let's say forward side, and then your fluorescence, and again area, height, width, and available for these parameters. Polychromatic flow cytometry, what does it mean? Like in a one time, you can do multiple colors, more than five, or and you can do the analysis of all those colors. It is, uh, I'll come to the application part. There, I'll tell you what does flow or polychromatic flow cyto means. But you can break it. Poly means multiple, chromatic means multiple. So basically, polychromatic is multiple color, where you use multiple color or multiple marker. At that time we call it polychromatic flow cytometry. Now the graphical representation in your machine, and it comes in different form: dot plot, contour, color density. In dot plot is general plotted, dot plotted population, which you generally see in your machine. Then comes the contour plot. Contour plot is like your contour farming. When there is a deep, or when there is a dense vegetation, if you see this, if there is a dense vegetation, it will form a cluster. And when the vegetation, like let's say there is a contour farming, where when there is a deep or like a dense vegetation, it will form a crowded uh, pattern. And when there is like less vegetation is there, then it will make a less cluster. So basically, in a simple term, it's like a cluster. It will form a cluster when there are a lot of population at one particular point. If you see this in dot plot, you generally won't be able to separate. Sometimes it happens that your population stick with your debris, and you won't be able to see where exactly your debris are, or where exactly your population are there. But if you see this graph, it's forming two cluster, and basically in contour you get the cluster. uh, and this is for your monocyte cluster, this is for your neutrophil cluster. And in color density, it's the same concept, but with some more color. The the more will be the population, or more will be the cell, the more brighted or more dense color you'll find in that particular area. And then comes your 3D plot. You can see the population in 3D form. And I'm going to show you all this in your machine as well. That will be even much more better. I'll show you how does it look like in machine. So again, we are talking about lysol blood, uh, your lymphocyte, monocyte, and your neutrophils. Now let's go to the point called gating. How we do the gating, and it is very important for you. First of all, you should know the biology of your sample. At least a little bit knowledge of your sample before going to perform any flow cytometer assay. You should know a little bit of biology of your sample. At least you should know like what cells, what kind of cells you are using, because even if you are staining those cells, you need some information. So you should have a little bit of knowledge of those cells. Now you have a little bit knowledge. So let's say right now we are talking about the lice whole blood. So first we do the reasoning. Reasoning is like, let's say if you have a home and you have done a boundary, right? So that is your property. Now you allow, it's up to you which things you allow to get in or get out. So the reasoning is like boundary, making a boundary around your required or your interest of population of interest. Okay, first you region that thing. Then once you region it, after that you do the gating. Gating means you already region that population. And now in that population, you are searching other things. Let's say if we are doing a treasure hunting, okay, and you know that at particular area I am going to find all my clues. So you made a boundary that I am going to search in this area only. So same, I wanted to find my, CD19 T cells. Uh, so what I did, I made a region. I know in this population only, I'm going to find all this marker. So I made a region, and now I'm searching for those markers. So now I made a gate. This is called gating. This is called regioning. Okay, one more question for you guys. If this is CD19, if and this is CD3, 9% CD19 and 74% CD3, which means T cell, B cell. What are these 70%, 17%? Can anyone answer me that? What are these 17%? Can how how can we both? No, no, no. It's a negative, yeah, but okay, negative both, but yeah, yeah, negative both, and then CD3 negative, 19 negative. But I want to ask, what type of cells are them? If it's not CD3, if it's not CD19, what are these cells then? There must be something, right? If it's a lymphocyte, there must be something. Okay, just a general question. What does a lymphocyte have? If it has B cell, T cell, one more cell they have, right? NK cells, right? NK cells are, yes, they are not CD3 positive, neither they are CD19 positive. So whatever is there, those are your NK cells. Right now, I saw one question Kiran has asked. Uh, what type of cells or particle might correspond to the cluster with small FSC and SSC pulse? If I'm getting it right, Kiran, then so basically, a small, if I again I'm using the relative word, but a relative small cells. Uh, Again, I'm taking the example of lymphocyte because that is the best example you can see because that is a heterogeneous population. Or you can even take example of any small cells which are smaller than your lymphocytes or I would say you can take an example of your RBCs or your bacterial cells. They are even more smaller than your lymphocytes. So if they have even very small peak uh, and you know and cluster doesn't define the size. Cluster is like for example, you see the herd of the animals, they make a herd, they stay in a group. So it's same like that. The same kind of cells stay in a same group, same cluster. If I have given it right. If not, tomorrow I'll be coming. You can write this question and then we can discuss face to face tomorrow. Okay, let me first check what time it is. So I have another 5 minutes. I'll try to finish this. Then if you guys want a little bit of 5 minute break, then we can do that. Now, triggering the electronic, here comes your threshold. I'll directly go to your uh, this graph. What does threshold means? Threshold is a unit or is I would say the command we give to the machine that at particular point I want my debris to be removed. So uh, I think the technical person might know this even better. Uh, and tomorrow I'm going to show you even more clearly in the machine that how does this threshold work and what does this threshold means. But right now, please uh, do understand. So tomorrow it will be beneficial for you. Uh, so this is your debris. I gave a threshold of, let's say, some amount through which this debris got removed, right? But I have to be very careful so my population of interest won't get loose. If I'll give a higher threshold, it will take away my population of interest as well. So, right, what happen is, let's say you tell your machine to record some 10,000 events on 10,000 events of everything. Like everything means all of it, out of which some 2000 events are coming from your debris, and that is a waste. You don't want it. You don't want your signal coming from your debris because you can't do anything with that. You don't. And once you remove the debris, whatever 10,000 cells you have acquired, it is coming from your true population and true signal. Now, let's go to the compensation. Okay. Uh, do you guys need a 5 minute break or something? Uh, Ma'am, or should I continue?
Yes, you can take, I think.
Okay, I'll continue then. Fine. So let's talk about the. Okay, okay, thanks, Neha. Let's talk about the compensation theory. What does this compensation theory means? Now, just a minute. Yeah. So as I told you in previous slide that your sample has emission and emission and excitation spectrum. So basically it form a wave kind of thing. It not always a single line. It will form or a band kind of thing. And when it will form a band or a wave, there it will spill over into other channel as well. So FITC signal is spilling over in P, also in a little bit in Percp. And because of which, what happened? You see this graph. If you have done uh, any kind of data analysis for your flow cytometer, then let's say this particular sample or this particular tube have FITC only, nothing else, no other thing. So it should get only FITC signal, right? But as you see this, and now as you have given me a right answer for your CD3 and CD negative, CD19 negative, so I'm understanding that you know the concept of this thing. So if this means it is your P and FITC positive. So, but this shouldn't be the case, right? Because this particular sample has you know this particular sample is tagged or like tagged with only FITC. Like this sample has run just for FITC, but still you are getting a P signal and also a little bit of percp signal. Why? Because of the spillover issue. And this shouldn't be the case. For example, if it would be a CD19, it would be a CD3, then as you know the biology, there are no cells so far found that they are both CD3 and CD19 positive. It can't be happen, right? So it's mean there is something wrong. And what is wrong? It's the spillover issue. So to remove that spillover, we do the compensation. So compensation is basically a method to, remove the spillover. And how we do that? So in your machine, there is a compensation matrix or a spillover matrix. So there is a formula for that. What formula we use for that? Uh, that is unwanted minus percent wanted. There is this formula. You can write it down tomorrow. I'm going to ask you this, and we are going to do the compensation tomorrow live in machine. So there is this formula called unwanted, okay, minus percent wanted. You have to give, like, you have to give the value here, so it will do the compensation. Basically, it's removing the unwanted signal from your wanted signal. Okay, so what's happened now? Once they give the value here, so basically they are removing P signal from your FITC. So once they give the or, we give the value here. Now, previously it was showing something like this. After compensation, we remove the unwanted P signal in FITC, and now we got our pure FITC signal back. So we remove this thing. And one more thing, you see the value is 20 here, but now let's go to the per CP. The compensation, the signal was not that much, the spillover was not that much, it was very minimal. So just zero point 0.9 works very well for it, and it came down. Okay, so that is also, this value depends on how much spillover you are getting in your population. Now, how you set up your color compensation? When you use cell, it should be, you should have individual color tube, and then a unstained one. And for bead, it's the same, that you should have a unstained one, and then you should have an individual color bead. And then few beads come, which we call compensation, yeah, or com bead, calibrate bead, which are already tagged with the fluorochrome. I'm going to get those bead tomorrow. And 7 color setup beads, all of these are already tagged with the fluorochrome, and you can do compensation with that. And you have to adjust the voltage, PMT voltage, to set the compensation. That we are going to do tomorrow. That's why I was telling you that setting up the PMT voltage is important. And once you adjust the PMT voltage, after that you can't change it. Now let's come the question, uh, like how many cells per sample we have to acquire, and what is the criteria? Like, let's say someone is asking you to, record 10,000 cells or acquire 10,000 cells. What does this mean? Like, where this 10,000 comes? Why not we can do 50,000, or why not we can do 1 lakh? In what thing it's depend? So before that, so it depends on your, what is your population of interest, have, like how much population of interest you have in that particular area. For example, if it's your population interest is 2% or above, then the 10%, sorry, 10,000 of cells are significant, statistically significant for your data generation. For example, I'll take example of CD3, right? In your lymphocyte, your CD3 is more than 2%. So even if you want to see the, let's say, CD3, 10,000 event or even less than 10,000 is more than enough for CD3. But then 10,000 of that particular cell. So I know in my, if I'm going to do all event, it will going to include my, let's say, lymphocyte, monocyte, and all. So I'll somewhere acquire 20,000 or 30,000 to get the perfect CD3 value. And now if your population of interest, and now comes the part when you have a very rare population, at that time you should have either 50,000 or more than that somewhere around 1 lakh. So you at least get a proper population, which is statistically significant for your data when you are going to present it. Otherwise, let's say you are going to present that data, the first question will ask about this, how much statistically significant this data is. So that's why it's very important. Now, uh, so for FSC and SSC, when we talk about the cell size and granularity, there the scaling we use, it's a linear scale. Uh, I'll tell you what does linear scale means. But in case of blood cells like blood platelets, RBC, or bacteria, because these are very small, there you have to use the log scale. And in case of almost all uh, fluorochrome intensity thing or fluorochrome tag signals, there the channel should be at FL channel means fluorescence intensity channel should be in your log scale, except your DNA cell cycle analysis, because there uh, the dye binds to the DNA and it tells you the amount content of DNA or the number of DNA, not exactly the intensity of the fluorescence. Okay. So this is your simple signal amplification. It's the same thing like you do the you apply the PMT voltage and all. Also, again, I told you about the linear and log amplification. So for your linear, big why we use linear scaling, why we use log scaling. In linear, the difference is like 10 per, let's say one population, and in two population the linear is not that much, or the brightest and dimmest population difference is not that much, it is somewhere around 10 to 20 times. But when we use log, because in one log there is somewhere around thousand-fold change, thousand-fold. So in immunofluorescence assays, or let's say if you are having a negative and positive, there the difference comes in like thousands and hundred, like multiple thousand. That's why we use the log amplification. So we are done with the compensation. We are done with the basic of flow cytometer. I have one more slide to show you. Let me cover that also. So that will be the application part. There is a CST part also that I'm going to tell you tomorrow itself in the machine. So that will be better. Just a minute. So CST part I'm going to tell you tomorrow itself in the machine. Now let me open another presentation for you. There we'll talk about the uh, application part of it. So far, any question? Maybe we can do a quick question round. I hope you guys able to understand a few of it. Uh, any questions so far? If you want, you can open your mic also, because we don't have much of people. So opening your mic will work as well. I'll take just one more minute and then we can move ahead for the application, like flow cytometer application part. So I'm going to ask you question tomorrow when I'll be coming there. I hope you guys will be ready for that.
Yes, I think there is no any question and you can go forward.
Okay, sure. So now we'll talk about the application part. I'll be sharing my screen with you guys. Let's talk about the application.
Yes, yes.
Like what are the applications of the flow cytometer, uh, where you can use it. I hope this is visible to you all. Can you see the slide?
Yes, yes. It's visible.
Okay. Okay, fine, Ji. Thank you.
Yes, yes.
Okay. Okay, fine. Now, let's talk about the application part. I'm going to give you an overview of application part. Uh, so what are the application? So this is the application just for a brief application part in clinical side. So basically we have two application. One is for clinical, one is for your academia or for uh, let's say research. So in clinical, clinicians, pathologists use flow cytometer. You must have seen that so many uh, assay or so many um, let's say pathological assay they do, and also they run the patient sample, they get the reports. So they do this kind of assays there, and they run this kind of assays. So they do absolute CD4 cell counts to check for HIV patients, for joint pain and arthritis. They run the HLA-B27 assays. Leukemia and lymphoma panel they run there, and it's a pretty good one. They run somewhere around 11, 12 color panel, where they diagnose the blood cancer, or they diagnose the cancer basically. Then there is a solid tumor ploidy. They check whether it's aneuploid, polyploid, or like what is the ploidy, because you know that your cancer cell divide abnormally. So there are a ploidy formation there. Then PIDs, basically, they do the TBNK assay where they tagged yourself with T cell marker, B cell marker, NK cell marker. And for hemolytic anemia, they do the PNH and all, bleeding disorder for platelets, uh, transfusion and transplantation. Basically, they do the stem cell or CD34 uh, um, CD34 staining there to check for the stem cells. Also, they do the flow cross match, which is basically, if you know, HLA cross matching. So this flow cross match is one of the part of that HLA cross matching. They check whether the donor and the patient, they are perfectly matching each other or not, or whether there is a clash between them. So this is just a clinical one. I'll be talking more in a detail for the research part. So let's go to the research application. Uh, so research applications are, just a minute. Yeah, these are the research applications. So you can use it multicolor immunophenotyping involving for cell surface antigen, also for intracellular antigen. So if you remember, I was talking about multicolor or polychromatic flow cytometer. This is what I mean. When you use like multiple markers, multiple color in just one tube, uh, then that what we call the polychromatic flow cytometry. Then there is intracellular cytokine you can read. You might, maybe in future or maybe right now, any one of you must be doing this intracellular stainings to check the intracellular, for example, IL-6, IL-2, IL-17s, all this cytokine, TNF alpha, gamma, all this cytokine study you must be doing. Now, apoptosis, you might be using it for apoptosis also, like for P staining, cell cycle for the ploidy check, cell proliferation assay, CSES, and then other BFUs, all these things. I'll be going to cover all these things in detail also. So let's just go through it. The cell signaling, physical cell separation using the cell sorters and all. So what are the immunophenotypings? You can in one tube, in one particular in just one tube you can run multiple immune marker. You can do the immunophenotyping, which is like you can separate all those immune cells, like let's say CD3, CD8, CD4, CD19. Basically you are doing a phenotyping of those immune cells. I have given you this example. Uh, Also, you can tell the binding sites, means the more the fluorochrome intensity for that particular marker, the more will be the binding site. As I have given you the example of CD45, it's mean, let's say in lymphocyte, the uh, in lymphocyte, let's say the CD45 is more than your fluorescence intensity is more in that as well. Okay, you can use it for the reporter genes also. What does this reporter genes means? So basically, maybe in future, or maybe either of you must be doing that transfection of cells, right? And you express your GFP protein, YFP protein, RFP proteins in those particular cells. And then you go to your flow cytometer, you check how much percentage of cells got those particular genes. So basically to check the encoded protein, to check whether your cells got those GFP expression or not, you can do that as well. So that this is for those reporter genes. Just a minute. There was a question. Sorry. Okay. Okay. Fine. Now, so these are for functional assay, where enzyme substrate assay you can do. You can do CFDSAE for your cell trafficking or cell proliferation. Uh, So there is this assay where the multiple peaks form, and generation to generation this dye transfer, and through which you get to know how does the cell proliferation is happening, like whether the cell is getting proliferate. So this dye transfer from one cell of generation, let's say a parent cell to the daughter cell, and through which you'll tell the whether the cell proliferation is happening or not. You can do the membrane potential probe for JC1. This JC1 is for your apoptotic membrane. This is generally in your mitochondria. So there you get to know, like for if there is a apoptosis of cells, at that time we use this JC1, pH probes, calcium probes, oxidative burst, or for ROS we can use this flow cytometers. So let's start with the immunology subset analysis, cytokine analysis. So for example, these are the example I was talking about, the even we call it the immunophenotyping or immuno subsetting. Uh, for example, this is your CD8 and CD4 cells, right? In your CD3 cells, these are your CD4 cells and these are your CD8 cells. And then they differentiate this CD4 into Treg, naive CD4. So basically you get your name. So these are your memory markers. You can tell that these are, so this is actually pretty interesting when you go a more when you're going to read a lot about immunology. This is pretty interesting study in case of immune responses. For example, the vaccine response. For example, you are doing any study where your cell mediated immunology come. This is very important there. Uh, this is your Tregs. It is also very important in most of the autoimmune, in your cancer immunology. Then your CD8 memory and Treg memory, in memory, your central memory, effector memory, TAMRA. So this is all very important. So flow cytometry has a power to, give you the knowledge about all these things. Now comes the cytokine part. You have Th1. In Th1, you have your, just a minute, just a minute. Yeah, can you see this screen? Sorry, there was some issue. You can see the screen, right? Can anyone confirm it?
Yes, yes.
Yeah. So in your cytokines, for example, Th1, it's a subset of your T helper cell. So Th1, Th2, and other Th17, there you have different cytokines. So basically, a pretty decent, simple example. When you get sick, right? You get a fever. So basically, your immune cell get activate, right? So your fever generally comes from your IL-2, and also from other things, but IL-2 is also a major cytokine which cause you fever, and that particular cytokine is also involved in your different things. Then comes your Ch2, sorry, Th2, your T helper cell type 2. It's come in your humoral response. And then Ts17, which is your inflammatory markers, inflammatory cytokine. So this all of this study you can do using flow cytometer. And then again, for example, you do it in ELISA, all this cytokine study, but you can do the same in flow cytometer. And PT has one of the best uh, kit for it, where just with the 50 microliter of your sample, you can do all this study. The kit comes with the name of CBA assay kit. There you can do all Th1, Th2, Th17 uh, cytokine studies. Now come to the protein phosphorylation or cell signaling path. So there is, when there is an activation of cell, at that time proliferation happen, phosphorylation happen. For example, tyrosine phosphate get phosphorylate, and tyrosine kinase get phosphorylate, your STAT3 get phosphorylate, and these are the cascade through which your cell get activate, right? Your cell, when one cell interact with another cell, at that time the cascade happen, the activation of cell happen through phosphate. Basically phosphate gives you like, it's like a power, how like ATP comes in, it gives you the phosphate, it activates those cell. All of those things you can find out using your flow cytometer. How? Let me show you. Also, for example, few people do the phosphate assays or using the Western blot. For example, they want to see whether in Western blot they check out that whether the particular cell got the phosphate or not using some particular antibodies. But uh, these are the classical method, as again I was talking about, like they use the SDS or Western blot for the phosphorylation, right? And in classical method, whatever signal you are getting a whole signal. Let's say, for example, if you see this one, sample 1, 2, and 3, in 1, there is nothing. So again, there is nothing in Western blot. In sample 2, there are, let's say, 5 cell were having a signal of, let's say 5 cell were getting phosphorylated, right? And they were showing a signal which is cumulative equal to 50. Okay. Now, in your Western blot, still is showing the same band for your second sample and the same band for your third sample, which is coming from just one cell. One cell is showing 50 and still showing the same, band for that. But in flow cytometer, it's not the case. If the signal is coming from the 10 cells, if you see the intensity of the peak, so these are your cell numbers. In your y-axis, you have your cell numbers. So it's telling you the cell number as well, that how many cells are showing that particular protein. And if you see the third sample, as one sample of cell was showing the uh, equivalent, a signal which is equivalent to 5 cells. So you can see that as well. This is the beauty of the flow cytometer, that you can do the study at cell level basically, because you can't do uh, this kind of technique in other method. You can't do it in Western blot, you can't do it in any other method, but in flow cytometer, you can do the study at the single cell level. These are the basic phosphoflow process, how you do the phosphoflow assay, like you fix it, permeabilize it, because generally all why permeabilization, it should go inside, your antibody should go inside the cells, then stain it, analyze it, and you get the data like this. These are the basic phosphoflow kit. T cell comes up with the kit, phosphoflow kit. Okay, and then for example, this even there is one more beautiful thing in this, that you can see at what particular subset the phosphorylation happen. If you see this data, if this is your CD3, sorry, this is your STAT3, and this is your STAT6, okay, and these are your CD3 negative, CD20 negative population. So this is your CD3 positive, this is your uh, CD20 yani ki P cell, and your T cell. So if I talk about this one, so STAT3 is getting activated in your T cells, and STAT6 is getting activated in your uh, you know B cells, and this is your, sorry, this is your T cells. So it's basically getting activated in your T cell. If you say this one, uh, this is your T cell, this is your B cell, and this is your negative population, which means basically your NK cell. So you are getting STAT6 activation in your T cells. Basically, this is untreated, this is treated. So after treatment, you see there is a activation of cells, there is a phosphorylation of the STATs. Again, STAT is I would say it is inside the cell. It's a protein which gets phosphorylate, and once it get phosphorylate, your cells get active. So this is what happening here. Now comes to the cytokine based array. I was talking about the CBA kit, right? Where you can do the cytokine study. So for example, in ELISA or basically in ELISA, you do the sandwich ELISA, right? First, you coat your surface with antibody, then you put your antigen, it bind to that, and then you put another antibody which is tagged with a fluorochrome, and then you generate it. So same case here. In ELISA, you have to do like, you have to do 96 well plate all the time. You have to flip it, then do it. A lot of manual works come there. But in CBA kind of assay, you have to do nothing. You just have to make a cocktail, adding some buffer. Then you have to put your sample in that. Then you have to add another buffer in that. Finish. You got your sample ready. Now you have to go to the flow cytometer, and then you have to read it. So this is how your CBA assay look like. For example, this is your IL-8, IL-6, and these are other interleukins. But as there is a higher signal for this, cytokines, these are, as there is a higher signal for this, so this particular sample has a, this much of, and through some calculation, we have a software with us through which we can tell you the exact amount of those cytokines, that this much of cytokine, like in picogram, this much of picogram of cytokine is there inside the sample. And with a one go, you can do multiple cytokine analysis. Okay, as I told you, just 50 microliter of sample is required for your, uh, you know, for your analysis. These are the benefits. Like you can use only 50 microliter of sample. It's very fast. ELISA take like 4 to 5 hours or more than that. I mean, a lot of time ELISA takes, but in your uh, CBA, it's just 3 hour incubation is there. Within a 5 hours, you'll get your data ready. You can even analyze it. I'm talking about the whole thing, like from the day of starting till you'll get your data in your hand. Just in 5 hours, you'll get it. Okay, and you don't need multiple vials, multiple things. In just one simple tube, you get your all standard done. Okay. You can go for like from 10 to 2 to 10 picogram of standards. Okay, these are the publication they have done using the CBA kit. Now application in microbiology. So okay, first we'll go to the immunology part. So you can do the T cell enumeration, means you can count the T cells. So as I was talking about before this, I was talking about like the relative fluorescence intensity or a relative count or a relative size. But again, if you remember, I have mentioned using beads. Either you can get the absolute count, absolute size. So to get the absolute number, there is a thing called true count bead by BD that will tell you that this much of cell, exact number of cells there inside that sample. For example, exact number of CD4 cells inside a sample. It will tell you that as well. Now comes to the cell viability. It's tell you the cell viability, how much viable cells you have in your sample. Uh, so for that, they have a cell viability assays. You can use the viability dyes. You already using it like propadium iodide, 780, TO, thiamine orange. This is so it bind to your DNA and RNA both. And this TO has the ability to bind the live cell. Generally, if you have seen, all dyes bind to the most of the dye bind to the dead cell. Basically, your cell, whatever dead cell is there, the dye will intercalate inside that and then it will bind it. But TO has ability, it can bind to your live cells. And you can see this one. This plot tells you that these are the live cells. These are either injured or somewhere, going to dead. Either it can be because of necrosis or because of your apoptosis. For cell proliferation, as I was talking about the CFSC, like it's a dye which transferred from one generation to another. So if you see the case of live cells, the multiple peaks are formed. This peak, which tells you that the cells goes from the different phases, like the different phases happen, right? uh, but here if you see, there are not that much of peaks are there. So basically your cells are dead. There is not much of uh, you know uh, like generation of peaks, so there are not much of phases there inside the cells. So if there is not much of uh, phases means, for example, when the cells divide, it has a different phase, like like telomere phase. In mitosis, a lot of phase are there, anaphase, metaphase, all these phase. So all of these peaks come for that. Sorry. Now comes the cell cycle analysis. So as I was talking about in the previous slide as well, that we have uh, G1, G0 phase, and then we have S phase, and then we have a G2 phase, right? So in G1 phase, your cells are having a haploid, and once it go to the G2 phase, then there is a synthesis phase for the DNA replication, and then once it will go to the G2 phase, the DNA content get doubled. So these are the dye we use for that. For example, these are your G1, G0, G1 phase, and this is a typical gene. Uh, this is what a normal cell looks like. But this is cell cycle analysis is very important for the pharma companies. Whenever pharma companies uh, go for drug discovery, which affect the cell cycle, you must have heard about the few drugs. I am not recalling the colchicine is one of the example for that. It arrests the cells at M phase. So you'll get a lot of G to M phase. For example, let's say if a drug is, hindering somewhere in synthesis phase, what's gonna happen is the peak for G1, G0 phase is so much that it will not move forward, right? So these are count. When a drug target your S phase, when they target your S phase, then it will not go to, so it actually block the S phase. Now your cell is not moving forward. They are not able to move forward from like from your G0, G1 phase. And now they stuck here. So you'll get a lot of peak. For example, in this case, they have used a dye which are targeting your, uh, M phase. I mean, it must be a colchicine treatment, so you are getting a lot of cells in your G2 phase. Like all cell from G1 comes to your G2, but now they are not moving forward. So it's mean they have treated with some drug which is targeting their M phase, so your cell get restricted at G phase. Okay. Uh, Now comes the PRDUSA. That is also there to check the cell cycle. It's the best example for your G2 phase. Like it's one of the good assay to check your cell proliferation. Cell cycle analysis. It's good for your S phase basically. Now comes the apoptosis part. You can do the apoptosis using flow cytometer. How you can do that? You might know apoptosis, and it is like a vast topic for the research. People do a lot of research in apoptosis uh, because I would say in every disease, every chronic acute disease, there is a cell death happening. Even in normal life cycle, even in normal life cycle, right now inside me, inside everyone, there is apoptosis happening because the cell get aged, and that aging of cell after certain time it will get apoptosis, like the cell become apoptized, and then it will dead. There is a like automatic death. So this is a vast topic for it. So, and flow cytometer is one of the best technique for apoptosis. How come? This is the example. uh so for early apoptosis, you can use annexin and pi assays. For mediate, you can use JC1 dye, which actually tells you the mitochondria changes. uh, so apoptosis happen in the stages, right? uh, First your cell will start folding, and when your cell wall gets start folding, there is a PS protein, which or phosphodilate serine, it will start coming to your cell surface. And then after that your mitochondria start showing some changes. It starts showing JC1 protein in there, in mitochondrial structure. Then there is an expression of caspase protein, and in the end there is a breakdown of your DNA. So using all this thing, you can use your flow cytometer in this case. So let's take example of each one by one. So these are your JC1. So basically early apoptosis detection. So if there is a high level of, for example, if you see they have treated uh, something, and then after something means, let's say, fastmap, camptothecin, and another drug, sporine drug. Uh, so you see that in control it was fine, but after treatment, the uh, the cells start, uh, and the apoptosis has started. This is the another example where they have used the caspase 3, which is come in between the mediate, or it's like a mid. Uh, so there is an early stage and there is a mid stage. So this is like a mid stage apoptosis, because then the caspase proteins start expressing inside the cells. So if you see, in untreated, there is no caspase protein, but after the treatment, the caspase protein start showing up, which means either these cells are like they are, so basically these cells are getting toward the apoptosis side, they are going for apoptosis. Same goes for your pi and enzyme staining. uh, they have shown that when they are treating, like through the time, what's happening, if you see, like this is 0 hour and this is 5 hour, so these are your live cells, they are going toward the apoptosis site. So, and these are your in between, these are your dead cells, they are your apoptotic cells, they are like almost dead, they are more toward the dead side, and now tagged with pi means the dead cells. So your cell get dead after like 5 hours, this much of cell get dead. Tunnel assay is for your DNA. So as I showed you there in the previous slide, this one, your DNA also get damaged when there is a apoptosis going on, or when it's in a stage of apoptosis. So you can use the tunnel assay there, your DNA get break, and in tunnel assay they bind it, basically your this BRDUTP, it's like it's an analog of your thymidine, and it's bind to your those nicks. It's so when the DNA get break, it form the nicks like a small break sites. There, this BRDUTP binds, and it is labeled with the fluorochrome. And more will be the binding of this particular uh, enzyme or particular, let's say, yeah, a particular enzyme. Then more will be the signal, and more will be the signal means there is a more damage in your DNA, and it will show you that yes, your cell is about to die because its DNA is damaged. So these are the example of it. Now comes in stem cell, flow cytometer in stem cells. So I think you must know what use the stem cells for identification of drug, toxicity testing, and there are different types of stem cell: pluripotent, multipotent, unipotent, embryonic stem cells, and it can differentiate into different cells. So, and that is one of the, right now in the research field, it is one of the hot topic. So this is what we call the bird-like structure. uh, for using the forward and side scatter, there is this bird-like structure form, hummingbird pattern we call it. Using the host dye, there is this hummingbird pattern form. It show you the stem cells, that there is a stem cell formation happening, or there is a stem cell actually in let's say if you take out stem cell from the bone marrow. So this, when you stain it with the host dye, then this kind of pattern you'll see. There are the kits come for stem cell by PD. You can do multiple analysis, for example, cancer stem cells, hematopoietic stem cells, mesenchymal stem cells, and multiple stem cells kit are there in the market by BD, and you can use that one uh, for your stem cell analysis. Okay, these are the kit for that, for pluripotent and for hematopoietic stem cells. They have different marker, positive, negative marker to differentiate whether you have a particular stem cell or not. Then these are the stem cell flow kit. Now let's talk about flow cytometer and nanobiotechnology. As I told you that you can use flow cytometer in nanobiotech also. Many people are doing that already, and how it will be helpful. So there are, you make a nanoparticle. Now you are tagging it with cells in multiple ways. Either it's inside, outside the cell, you stick it on the surface of the cell. Either it's inside the cell, and the third and the last scenario is when it is inside the cell, and now that nanomaterial is tagged with some fluorochrome. So if it's outside the cell, then there is an increase in forward and side scatter. So if you take your control sample where is nothing, like let's say this one, uh, and you take this sample where your nanoparticle is bind around around the cells, then in that scenario, what happened is your cell size increased, right? And now if say your FSC increase, even the SSC also increase sometime, but majorly your FSC increase. Now, if the nanoparticle is inside the cell, at that scenario, the granularity of the cells increased, right? So the FSC might not change. It will remain the same, but your SSC will be higher than this one, your untreated one. Now, if you have tagged it with some fluorochrome, that will be even great for you. You can see the, fluorochrome is there inside your cell, and you can see the fluorescence intensity increase. So that's how you get to know, like, the particular stem cell is, sorry, particular nanoparticle is stick or get inside the cell. Now in plant biology, it is very helpful. So we use it for like ploidies, because plant has multiple ploidies. Like we human have few ploidies, but plant go for like multiple ploidy, triploidy, quadruploidy. They have multiple ploidies. And to get a proper crop, we need all these ploidies. So you can count the ploidies using flow cytometers. These are and ploidy, how you can check? You can check it through the uh, cell cycle analysis, because in cell cycle the ploidies comes, and from there you can find out like what ploidy is that. So uh, there is a control, so there is a formula for that, you can find out with that. And also they have a control, a deployed standard control. Using that deployed standard control, they find out the DNA index, and using that DNA index, they have given a date, like a chart. They tell that if the DNA index is lower than 1, no, sorry, 1.5, which is equal to 1, it is deployed. If it's haploid, then it's 0.5. If it's tetraploid, then it's 2. If it's aneuploid, it will be never 1. Hyperploid, it is more than 1. Hypoploid, less than 1. Okay. You can even determine the DNA content of your. So basically what they do, they make the transient crops there, or GM crop there. So they want to see whether their DNA is really, get inside that particular crop or not. So to check that, they use this kind of DNA study methods. Now comes to the flow cytometer application in veterinary science. So basically for animal science, you can use it for immunophenotyping like we use it for humans. You can do the uh, for the sex breeding, for the breeding also, like you can sort the Y sperm, for producing either a male or a female uh, uh, cattle basically. So how you do the sorting? So there are sorters available. You can, sort those X and Y, and now this Y you can so basically you label those X chromosomes, Y chromosome, and then X chromosome, and then you sort it out, and then you inject it inside the female or in a surrogate mother, and through that you either get a female calf or a male calf. It depends. And these the sperm, a bull sperm look like this in your flow cytometer. So, okay, this is the end slide. Uh, so these are the basic uh, application part. Apart from that, you have any question, I would like to take it, and then we can finish this session. Just, I hope you guys have understand so far. I know it's a big lecture, like for 2 hours, but I'm like, if you guys have any question, you can ask me. And if you want, you can write it down also. Tomorrow I'll be coming to your place. We'll be demonstrating you. I can see the lyric behind sir. So we'll be doing the essay tomorrow and the lyric.
Namanji, can you, so you
Yes,
have
ma'am.
stopped sharing, right?
Yes, ma'am. Yeah,
Okay,
you want me to
excellent.
share? Yeah,
No,
I'll.
no, I don't want. I just wanted to tell the students who are there, especially Sanjana. I know you are in the PG, so I'm sure you can also come, you and Anjali. Sanjana, are you there? I hope you are there. Okay, excellent. So you are there. Then, apart from you, Neha, you are there. So all the students who are hostelers or who stay nearby, of course, you all have to come. And about Nandita and few others who are day scholars, if possible, please come and join because tomorrow Namanji is going to be with us in the institute and he is going to show hands on how all the things he talked about is done so that you have a real idea about those psychometric experiments, which will be immensely helpful for your research afterwards and just for knowing how it works. Okay, so I urge you all to come down to the university tomorrow if possible and join us for another session of hands-on training on flow. And so again, if you have any questions at the moment, you can ask him. Else, if it comes to your mind later, then please write it down and tomorrow you can discuss with him when you meet him. Is that all right, students? Okay,
Yes,
then
sir.
thank you so much, Namanji. And of course, we look forward to seeing you tomorrow at the
Yes,
institute.
ma'am.
And you have said that you will be coming around 11. So, students, he is going
Around
to join us
11.
at 11. And then again, he is going to resume this session hands on. And can you please tell us around what time you think it will get over, just so that the students have some idea?
So I'll get the beats with me, ma'am. So what I'm going to do is, if I'll come around 11, I'll try my best to reach there by 11 if there is
Mhm.
no traffic at all.
Right.
So by 11, if I'll be there, within a first half, we'll be done. And after lunch, we can take a hour, like by 3 or by 2. By 3, it will be done. I'm just, by 3 means if I'll take another 1 hour, then by 3 it will be done. It will not take more than that.
Fine, fine. Thank you. That will work just fine. And okay, then we will all see you there tomorrow.
Sure,
Hasib,
ma'am.
you want to say something? Fahim, you are going to be there tomorrow, right? Maybe he can't hear me properly. Never mind. So,
Yeah,
Namanji, we will see you there tomorrow. And thanks
sure,
so
ma'am.
much for this session today.
No worries, ma'am. It pleasure of mine. I'm happy to
All right.
share that.
Thank you
Okay,
so much. Then. Bye.
no worries. I think he is saying something.
Right. No problem.
Uh,
We will see you tomorrow. So the
Okay, ma'am.
students are also thanking you.
Thank you so much. It was a nice. Sorry, my throat is
One
a bit
request to all
down.
of you. One thing.
Yeah, हाँ जी पूछिए फाहिम जी.
I want I want to request to all of you, please switch on your camera for attendance.
Students who are there, please switch on your camera. We just want to take a group photograph. Hasib is going to take a group picture
Yes,
for
yes, yes,
records.
yes.
Sumit, Nandita, Sanjana, everybody. Neha, good to see you all.
Okay, okay, okay.
Hasib, you have the picture?
Just a minute, ma'am. Yes, yes, yes.
Thank you.
Yes, ma'am.
Thank you so much, everyone. Uh,
All
so
right.
Yes,
We'll
we
see
we
you
have
all tomorrow.
yes, I
will see you all
have
tomorrow. Yeah.
Bye.
Fahim sir? Hello. Hello. Fahim sir?
Are you listening to me?
Yes, yes. I just want to know this link will be continuing or you want me to close this link? I'm the host of the from Noida Industry.
No, no. It's you can close it.
ओके अभी और तो नहीं है इसके बाद कोई
नहीं नहीं कोई नहीं. There is no any program after this.
ओके सर ओके
Okay, thank you very much.
थैंक यू सर